Supriya madam, it's starting. Anything is there?
Yes, sir. Live ಕೊಡ್ತಿದ್ದೆ. Okay. Hello, everyone. Welcome to another exciting session of Creative Online Weekend Talk of episode 136. It's great to have you all here. Curious minds gather once again for another session of learning and exploration. Today's we are driving into the interesting topic, why Li-Fi when you have Wi-Fi. We will explore the difference between these technologies and what they mean for our connected world. Remember, creative is all about thinking creatively and embracing new ideas. Let's challenge ourselves to think differently and spark innovative discussions. Whether you have joined us in person or from YouTube channel Creative GBD, your participation makes our talk richer and more engaging. So let's start our today's session. And I welcome today's speaker, Dr. Satish sir, for this session. And I welcome all the participants for today's session. And I'll introduce today's speaker, Dr. Satish RN. Is an assistant professor in the Department of Electronics and Telecommunication Engineering, Siddhaganga Institute of Technology, Tumkur, since 2007. He received the BE in Telecommunication Engineering from KIT, Tiptur in 2006 and MTech degree in Digital Communication Engineering from BMS College of Engineering, Bangalore, India in 2011. He has submitted the doctoral thesis titled Towards Practical High Throughput Laser Based Indoor Optical Wireless Communication System at ECE, Indian Institute of Science, Bangalore, under the guidance of Professor Varun Raghunathan. His research interests include indoor optical wireless communication and agricultural technology development. We are very happy to have you, sir, and I welcome once again for today's session. Over to you, sir. Satish, sir.
Thank you, ma'am. Thank you. Am I audible?
Yes, sir.
Yeah. Thanks for the nice welcome and the introduction. Just to begin my talk, the title of the talk is Why Wi-Fi when there is Li-Fi. So it may be a general talk to all kind of audience, as informed me. So these are the wireless communication technologies. The Wi-Fi is a very well-known technology, wireless fidelity. And the next technology, upcoming technology is light-based, which is called LiFi, light fidelity. The question arises is when there is existing technology like Wi-Fi, why do we introduce a new technology called LiFi? So that can be a question. Or I had a mindset like, why Li-Fi when there is a Wi-Fi? That means when there is new technologies coming, can we forget the oldest technology? So we can frame the question in two ways, like why Wi-Fi when there is Li-Fi, or why Li-Fi when there is Wi-Fi. Both can be answered. Let's understand, and while concluding, we'll understand more about it. Yeah. This is the agenda of my talk. I'll briefly introduce what is Li-Fi, and then what are cellular generations and expectations from the cellular generations, and what are the potential enabling technologies to meet up the current challenges in cellular requirements, and what is optical wireless communication, talking about needs of wireless communication, and what are the typical use cases, that is applications of this optical wireless are aspects like solid state technology, how it is supporting the development of a new technology in wireless called optical wireless communication. And lastly, I'll brief about my work in doctoral submission. That is major two works I'll describe. That is system level demonstration of real-time multimedia bidirectional data streaming over laser-based indoor visible light communication. And then I also describe about RF and LiFi coexistence, a hybrid model. And then I'll conclude all about my agenda, what I have. Yes, let's come to the introduction of LiFi. Many of the audience may be knowing already, or some of you may be new to this. The LiFi is abbreviated as light fidelity, like the Wi-Fi what we have. Coming to the history of it, it's coined by the pioneer in the technology by name Professor Harald Haas. He gave a TEDx talk in the year 2011, where he introduced the concept of the data transmission over light. Normally, what we think is like RF is the source of data transmission or the media of data transmission, like it may be WiMAX, Wi-Fi, or cellular communication. But he changed the perspective of data transmission or wireless data transmission with the existing infrastructure called the light infrastructure. Normally, this technology is basically for the indoor transmission, wherein we have the infrastructure with illumination with the usage of LEDs. Nowadays, all incandescent bulbs are replaced with LEDs. So usage of this infrastructure based on LEDs, can we come up with data transmission as well? So it serves the dual purpose of communication as well as illumination. So that was the concept what he had in mind, and he came up with the concept called LiFi. So he is termed as father of LiFi. So that's why the name was given as LiFi, and I mean it is followed with the terminology of Wi-Fi, which is wireless fidelity. So other terminologies what we use technically is optical wireless communication. Normally we have heard of wireless communication or optical communication. We have heard two different areas of communication: optical communication or wireless communication. This is an area where we talk about optical wireless communication. Communication wirelessly using the optical media. So this is the concept. So in the commercial way, we call it as LiFi. In the technical aspect, it is called optical wireless communication. I'll describe why it is optical wireless communication. Or there is another nomenclature called visible light communication as well. So the name optical wireless communication is given because we use the wide optical spectral window of from near infrared to visible light. So therefore, we call that as a optical wireless communication. So there is another one called free space optical communication, which is used for long distance communication. Just a minute. So that technology is called free space optical communication, which is used for long distance link. And there is one more familiar concept called visible light communication, where we use only the visible spectra of the optical spectra for the transmission of wireless data. So which is termed as LiFi or Wi-Fi. I mean LiFi or VLC. So the main purpose of this is which serves the indoor short range access solutions. So we can clear about these technologies, sub-technologies of optical wireless communication, like FSO, which is free space optical, which is used for long distance communication, and visible light communication, or LiFi, which is mainly used for short distance communication. So there is a YouTube link in my presentation which talks about the TEDx talk which he has given. So next is I talk about cellular generations and expectations. The main concern about any generation of cellular technology is the growing demand for bandwidth in mobile communication. The reason is number of users are growing significantly, and the next generation wireless communication systems, they basically required to offer high capacity to support various broadband wireless services. And coming to the existing technology in India, which is 5G, so that is almost in the underway of deployment. So this is for the these systems boast significantly more functionality than the fourth generation. That means whatever the capabilities 4G technology had, so 5G should support 4G as well as support some other futuristic things about the upcoming technology. So here we can see in this picture, we can be very clear. The 3G and 4G technologies were mainly talking about the data for mobile, whereas the 5G technology mainly talks about the data for mobile as well as wireless data for household applications, wireless data for long distance transmission, wireless data for vehicle to vehicle communication. So it covers all aspects of data communication. It may be we call vehicle to vehicle as V2X, or like wireless to the home kind of technology. So that means upcoming sixth generation system has few core problems that require attention, like it has to solve higher system capacity, higher data rate, low latency, high security, and the data that is reaching the user should be with high QoS, quality of service, compared to the 5G. That means every upcoming generation of wireless needs improvement in its services. So which are the potential enable technologies to solve the upcoming technologies? So let's first see what are the expectation from any of the new technologies. Like let's have a comparison table in terms of the 4G, 5G, and the upcoming 6G globally. So the main parameters which are required, I have listed in the column number 1, like peak data rate, peak spectral efficiency, user experience data rate, area traffic capacity, latency, connection density. Say if peak data rate for a given user expected in 4G was 1 Gbps, so in 5G it is 10-fold, and in 6G expectation is 100-fold, reaching up to 1 terabits per second of peak data rate. And peak spectral density per hertz of bandwidth of any wireless technology should support 10 bits in terms of 4G. That should be triplicated in 5G, and that should be triplicated 3.3 times, that is reaching 100 bps bits per second per hertz in 6G technology. Coming to user experience data individually, he must get at least 10 Mbps data rate. It should be 10 folds in 5G and 10 folds again in 6G, reaching up to 1 Gbps of data rate. So area traffic capacity, the maximum area handling capacity of any cellular technology, is also reaching 100 folds. And very important aspect of any communication technology is delay in transmission or latency technically, which is tolerable up to 100 milliseconds in 4G, that should be reduced up to 10 millisecond in 5G, and still reduced up to 1 millisecond in 6G. So the next one is connection density. It should be again 10 folds, like many devices in kilometer per square area of any geographical region. So that means why these devices are increasing, it may be IoTs or any of the sensing devices that globally exist all over the earth. So these are the challenges we have in, or the expectations we have in any of the upcoming technology. So who will solve? Question is, who will solve? Like, what media will solve these challenging problems? So the basic solution is from the wireless access solution aspect. We go with ultra large scale antennas. Of course, antenna design area is one of the solution to address many of the issues here. And orbital angular momentum OAM based technologies are also one of the solution. Coming to the resource part, like uh, spectral part of the technology, it is from the RF end, radio frequency end, it is millimeter wave called as wave technically. Terahertz is one of the solution that is coming up in 6G technology, introduced in 6G technology. And from the optical domain, it is visible light or optical is the solution to address all these challenges. That means uh, whatever the area I'm talking about, like optical wireless or visible light communication, or the commercial name called LiFi, is not at all introduced to any of the standard like 4G, 5G, 6G, but it is in the way to introduce along with the upcoming technologies. So these are the challenges we have, as well as the solution from the visible light communication side. So what does this these potential enabling technologies address the issue? Like in this picture, you can see uh, we normally get the high data rate with optical communication, that is optical fibers, which carry more than 100 gigabits of data per second. But while reaching the endpoint, that is the user, wirelessly, our current solution is RF. We have the RF access points. That limits the user to reach the higher data rate. So that means you can see this black links which are connecting the users. So these are the limited links compared to any of the backhaul, like the fiber to home linkage. So that means either we should go for terahertz, millimeter, or VLC. I'll describe what VLC will in what way VLC will support as the high data rate between the access point and mobile user. So mobile and wireless devices traffic data has increased tenfolds, I described, whereas fiber can bring you up to terabits per second. So we have the passive optical networks which can deliver up to Gbps. That means the backhaul is ready to deliver you, but the access point is the problem because it is the current RF technology or the Wi-Fi technology. So to explore this, we need new technology. So let me highlight what is optical wireless technology. So the basic simple definition of optical wireless communication is sending information rich optical radiation over free space channel. That means we modulate the data over the optical signal and then transmit in free space and receive it and process it and reach the receiver. So that is the uh, crude way of saying what is optical wireless communication is. So that is embed the data on optical media and then receive at the receiver over a free space channel. Why there is a need of indoor wireless communication, and why it is getting more importance? The study says the number of users, wireless users, increasing up to 80% who will stay indoor for a maximum duration compared to 20% of the user who stays outdoor. That means there is a more demand for the 80%, like 80% usage of indoor data compared to 20% usage of outdoor usage of the wireless data, which makes us to think about an area called indoor wireless communication, which should be enabled with all these upcoming generation technologies. So therefore, there should be a potential solution from optical side. So here you can see the optical spectra ranging from radio waves to gamma waves. So what are we going to use? So here we are going to use the range from uh, say you can see the arrows like radio waves, microwaves grouped, and you can see the colored spectra, which is visible light spectra. If I use only this spectra for my optical wireless communication, we normally called as visible light communication, which is visible to naked eyes. So therefore, if I use this spectra and compare that with the RF existing uh, radio spectra, so we will get a bandwidth enhancement of 2600 times. So that means there is a huge bandwidth and there is a scope to look for data transmission over VLC. So there is one more way. If you include the adjacent bands like infrared or ultraviolet, so it is much more like 10,000 times. So that means there is a huge focus to look for this optical spectrum. So now we can be clear, like if I won't use only visible light communication spectra, it is termed as VLC, visible light communication. So usage of this spectra. If I use infrared or ultraviolet band, so that is in general it is called optical wireless communication. So that's the clear difference between VLC and optical wireless. But in generally we use the optical spectra in both. So optical wireless spectra includes visible light spectra as well. So therefore, in terminology wise, we are very clear. Commercially, it is called LiFi. Technically, it is optical wireless communication. Or in general, it is visible light communication if I use only the visible light spectral range. So here in the next diagram, you can see a very clear picture proposed by these authors here. Any cellular technology reaching each individual at home. So the technology they proposed for 5G model, wherein which we have a an antenna which is covering certain geographical area, which has so many households, factories, offices, buildings, etc. So if this wireless data reaches household, so that is the general RF way of communication. But each household has connected with fiber backbone. So fiber backbone is reaching the house, and then we have a terabits of data connectivity at house. But if I want wirelessly, so there is only solution as I described spectrally. We have the visible light communication way. Like we do transmit the received signal from the fiber and then use an access point called visible light communication access point. We call it as VLC access point. Instead of RF access point, we'll have a VLC access point, which is nothing but our LED source, or I'll introduce laser source as our illumination source, and that will provide us the Gbps of data rate. So this simple model will tell us how VLC will be introduced in the upcoming technologies. So here you can see another forecast, like what are the different expectations from upcoming technology. This diagram I took it from a forecast for 4G technology and how a LiFi or a VLC can be an add-on for the 4G technology. One thing is should be very clear: a new technology is coming up in any generation. It cannot stand on its own. It should be supported by the previous technology. So that means we call that way as coexistence. The previous technology exists, and the new technology coexists with the current technology, and they do have a handover between them. So here we can see the gray area, which is supposed to be supported by the LiFi region, and this slightly white region is supported by 4G. What do you mean by support? Is we have an axis called latency axis on y-axis and bandwidth axis on x-axis. So 4G forecast was up to 100 Mbps, whereas if you want more from it, you have to go for LiFi domain. That is the aspect. If latency, that is minimum latency that is possible by 4G is up to 10 millisecond, and if you want beyond that, that is 1 millisecond, then LiFi should be there. So what are the typical use cases that can be addressed are like autonomous driving and service robotics, augmented reality, tactile internet, virtual reality, and mobile telepresence. So these are the typical use cases or application areas which can be addressed using visible light communication. That means to address these areas, there should be a new technology which supports us. So that's what I'll take up. Very important, I mean, my area of interest called mobile telepresence, so which I'll highlight more on this stuff. So this slide talks about now we are very clear like what is OWC is optical wireless communication, VLC is visible light communication, LiFi is light fidelity. All mean the same, but spectrally they are different. Or application wise, one can be long haul communication, which can be used for FSO, or it can be indoor. So in general, let's go for use case. I specifically go with indoor case. So as I listed, it can be autonomous vehicles, which uses all these technologies, augmented reality, telemedicine, or we term it as mobile telepresence, basically used for robotic surgery control, virtual reality, high definition video streaming and office space, airplane cabins, hospitals, power plants, gas processing. I mean, the last three may be hazardous places where VLC is required. So diagrammatically, you can see telepresence robot. I'll introduce more on this. This particular diagram talks about the existing infrastructure. You can see the LED infrastructure, which is for illumination, and each of the user is getting served uh, along with the data. And third one is a telepresence robot in an office space, which is talking to many of the employees. And the big picture to the right corner is an application of visible light communication in the area of hospitals. So where we can use the existing illumination infrastructure by visible light communication and use it for video conferencing or telepresence kind of robotic surgery. So what are the typical features which supports all these use cases? The thing is, what I described is like if I take the visible light communication, it is 2,500 or nearly 2,600 times bandwidth expansion compared to the RF. And the thing is, you can see very clearly from this diagram, each LED source is directive to the user, therefore we'll have spatial reuse. And very important is light cannot penetrate through the walls. It's very secure. I mean, we can reuse the same visible light spectra in the other office or the other corner of the building. So therefore, there is a spatial reuse available. And security wise, narrow beam width, as I described, You can narrow down your beam to your office space or the working table or the working bench, what you call. And then it is very line of sight requirement. This offers physical security from the other data transmission. And the third one is we are clubbing the data along with the illumination. We can claim it as it's an energy efficient way of doing the data transmission compared to the RF, because in the RF we should have a source for illumination which is power hungry again, and there should be infrastructure for RF as well. So therefore, since both things can be done by VLC, we can claim it is an energy efficient way. So coming to the aspect in the way of solid state technology or the VLSA part of it, what are the VLSA aspects which are supporting to grow in the field of optical wireless communication? Normally, the optical wireless communication is supported only with the technology called IMDD, intensity modulation and direct detection technique, which is generally used in any of the OWC systems, which means that you just modulate the intensity of the light, flicker the light. We call it as flicker the light, and that flicker has the information and receive it by the photodetector and do processing and extract the data. So the detection is called square law detection, usually with the photodetector. So in the next picture, you can see the different solid state aspects or the device aspects to address the optical wireless communication. Here, any transmission, we need a transmitter. In the full communication requires a transmitter and a receiver, and the material side. So if you look at the transmitter in our visible light communication, the transmitter is a light source. The general light source can be laser diode, LEDs, or micro LEDs, or OLED panels. So you can name many. Coming to the receiver side, we'll have avalanche photodiodes, OPDs, pin diodes, micro LEDs, micro photodetectors, etc. So there are varieties of photodetectors. Receiver solid state devices available. Variety of transmitter device solid state devices available, and the materials like I'll introduce you what these materials mean in the optical way, like phosphor, quantum dots, and perovskites, photonic crystals. So the next diagram will detail more about this. So we'll take one example of source aspect. So wherein which we talk about x-axis as modulation bandwidth in terms of megahertz, y-axis as data rate in terms of Gbps. So here you can see different solid state technology support different perspective of requirement like modulation bandwidth or data rate. So if you go with a phosphor LED, which can support up to 1 Gbps with a maximum bandwidth of in the range of 5 to 10 Mbps, megahertz. And if you go with RGB LEDs, clubbing different combinations of light sources in the LED mode, here there is slight increment in the data rate and expansion in the bandwidth. And an improved version of LED, which is micro LED, which supports up to 1000 megahertz with an incremental change in data rate, which is up to 1 Gbps. Whereas you can see the next technology, solid state technology, laser diode. If I use laser diode, which can give up to more than 100 megahertz, 1000 megahertz, 1 gigahertz, and the data rate is tenfold again, reaching up to 10 Gbps. So that means there is a trend line which is set by the different solid state technology. So in that way, we have to use different solid state technology to go with a different demand in the wireless data transmission. So what is the summary of this particular slide is? As there is a growth in or the usage in solid state technology aspect, we also can gain the data rate improvement in our optical wireless communication. So that means, in simple words, if I use laser as a source compared to any of the LEDs, my data rate is at least 10 times or 100 times the data rate compared to the normal LEDs. Why I'm highlighting this aspect is our work was mainly focused with the usage of laser diode as the source for data transmission. Normally, the LiFi uses the LED. So I'll just focus on the uh, previous works which are done with LED based optical wireless, and then I'll compare with laser based. So here is a one of the preliminary work which talks about LED based transmission. Here you can see the LED as the source, photo detector as the receiver, with the achieved transmission of 125 Mbps with 800 lux level of intensity and distance up to 5 meter. So the next one, here you can see uh, the lux level is 1200 lux, and which is again 5 meter of transmission. So in the next one, you can see the RGB color mixing. RGB color mixing, you can see the red is coming from this source, green is coming from the other source, and blue is getting merged. So you will transmit using 3 different colors as a single beam of light source, and mixing of RGB will lead to white light. You can see red is coming here, G is here, B is here, and as well as they are mixing the yellow. If you consider RGB part, even we'll get the white source. I mean white light as the light source, and then reaching the receiver, and we can detect the data individually. So this particular work by the father, Wi-Fi father of Wi-Fi, Mr. Harald As, who has demonstrated the data rate with this particular technology, RGB mixing, up to 15.73 Gbps, up to 1.6 meters of link length. The next thing which I talk about is the laser-based optical wireless. Here, instead of LEDs, we'll use laser as the source. Somebody may come up with the concept like laser is hazardous to health, or it will affect our eyes. We have the solution to overcome that. We remove the coherency part of the laser, which will be spread across the larger area, and the intensity is reduced, and we call that terminology as MPE, like maximum exposure power. So we will have a control on it. So therefore, we are safe in terms of health hazards as well. So with that key thing in mind, we can proceed with laser-based optical wireless communication. So this is one of the previous work with illumination and communication. So laser is giving the illumination as well as communication, which is proved up to 1 meter of link length, and with the concept of imaging receiver, they have worked on laser-based optical wireless. So there is one more work only talks about communication, where they have not worried about the uh, illumination part of it. So they proved the very highlighting work here is the increase in the link length, which is source to distance is 12 meters, which is not proved by any of the previous work. This 12-meter of source to distance is a pretty long distance with 2.5 Gbps of data rate with on-off, just simple on-off key. So that means for a 12-meter, around 35 to 40 meters, 40 feet of room link length, so the data rate of 2.5 Gbps can be achieved. So here is another work with RGB laser diode mixing with the generation of white light, so which has proved up to 8.8 Gbps. So with all these slides, what I can conclude is uh, either we go with the illumination separately or communication separately or communication and illumination together. We claim it as optical wireless communication. If it is specific, like I need illumination along with the data transmission, it is termed as visible light communication. Next, I'll move on to the very interesting use case of this optical wireless communication called as mobile telepresence robots. On the right side, you can see a diagrammatic way of representing mobile telepresence robot. Telepresence in the sense the actual user is somewhere and he is having a telepresence at the point where he wants to observe the data. Very important thing is he will have a camera, audio, multimedia connectivity to the robot. Basically, it's a robot with added high quality multimedia equipments, like it may be display, it may be camera, it may be audio. Everything is with the high qualities. High quality in the sense, in the aspect of communication, like high data rate or high resolution or high quality of the audio. All these are the aspects in mobile telepresence receivers. So basically, the technology is a video conferencing robot steerable from a remote location. That means you are somewhere in any part of the world and you are controlling, or you are presenting yourself at a given place over a robotic vision. So main requirements, as I said, it needs LED screen, web camera, microphone, and a speaker allowing communication between two parties. So the other terminologies for this technology is mobile telepresence or mobile robotic telepresence. You can call it with different sub terminologies. So what makes this technologies to have OWC or LiFi as an add-on? I'll just describe in the next term. So basically, if you look at the history of mobile remote telepresence, they were coined in the year of 2012 by Willow Garage. He basically develops hardware and open source for personal robotic applications. So the objective was to improve the work efficiency in company by monitoring the co-workers from a remote location. So he wanted to see how his office workers or garage workers are performing and when he is connecting from a remote location. So the prior to the existence of these mobile telepresence devices, he needed to have a phone conferencing or video conferencing. It may be a stationary way of communication, but it cannot be mobile in nature. But with that in mind, he made our later they pushed a laptop with a push cart, like some assistant is supposed to push the cart and reach the particular employee to converse with the boss. So he thought in that way, like, why can't I have robotic way of monitoring my employees? So that's how this mobile telepresence came into existence. So again, why MTP needs visible light communication? I have two of the use cases here, which mainly talks about usage of this. Just a minute. I have two videos to run. Yeah.
Sir, is there audio? Audio is there, sir?
Yeah, it has an audio.
There are three dots upside, sir. There you have to select share sound.
Just a minute.
Bar upside. Three dots is there, no? More option. Are you able to see, sir? More the mic start video, that bar is there, no?
Yeah.
There you have three dots like more. Click on it, sir.
Audio settings, you mean?
No, sir, no. Three dots.
Maybe
More.
it's not fitting my screen. It's okay. I mean,
Yes, sir.
even
Okay.
if it is not with audio, it works well. With the video, only
Narrate
you
it,
can
sir.
observe. Yeah. Here, the application is telepresence for remote patient care during COVID. This was the usage of telepresence devices for the doctoral care for any COVID patient. So you can see how the doctor monitors and suggests some medicine for the patients. So this particular person is a local assistant to the remote doctor. So during the era of COVID, we needed a social distancing, but this will offer, you can think of miles of social distance, not even 3 meter or 2 meter. So you can see the expert is communicating to all the local bodies over there, like doctors or nurses, to assist the patients. I may take little more time. More slides are there. So I think you're very clear about what is the aspect of these telepresence robots in the area of health. I'll move on to the next video. In this is a telepresence robot used in industry monitoring. You can see the boss is monitoring or conversing with all the employees. So the question arises is why VLC for mobile health monitoring? The very important thing is, I can literally say RF is banned in any of the health related areas. The reason is RF is comes up with electromagnetic interference, and the intrusion of this electromagnetic interference jeopardize the quality of the medical monitoring. The reason is the medical monitoring equipments also works with RF technology. Most of them uses the RF technology, and this communication technology makes more electromagnetic interfering thing in the aspect of medical healthcare or hospital equipments. So as to maintain the accuracy and efficiency of the data transmission. So this may become the crucial. So therefore, the RF is banned in the field of medical. So then how do we get the wireless communication out of, I mean, our wireless communication in the area of hospital or health monitoring areas? Is only way is to introduce VLC so that the existing infrastructure like LED source or laser source can be reutilized to transmit our data, and it serves the purpose of data transmission. So therefore, thereby overcoming the electromagnetic interference, which is the more general problem in the aspect of RF. So therefore, emission of RF radiation, that will deteriorate the health of a patient as well. So that can be the one of the key point why we go with the VLC, and as well as medical devices malfunction when we use wireless cellular phones. So with these ideas in mind, we move on to the usage of visible light communication for these health applications. So therefore, definitely we can claim these uh, mobile telepresence robots needs a technology which works with the visible light communication. So they normally work with RF or Wi-Fi. So the key concern is replace the technology with which it is getting the high data rate data with the VLC technology. So now I'll focus on my thesis work, part of the thesis work, system level demonstration of real-time high quality multimedia bidirectional data streaming over a laser based indoor VLC. So this uh, part of the work of my thesis was majorly to address the real-time data transmission over the use case like mobile telepresence devices. As I described, the mobile telepresence devices mainly require multimedia transmission like audio, video, or data. And I first addressed this aspect in this uh, first of my thesis. So the coming to the aspect of the work, it was end application of any communication system is transmission of real-time data like text, audio, or video. And the goal was to develop and demonstrate a laser-based visible light communication with high data rate multimedia streaming. The prior works, when we do any of the works, we look for the prior works what they achieved. It was basically majority of the works were LED-based works, reaching up to 37 Mbps with LEDs. And this is the prototype implementation, which went up to video broadcasting with 2 Mbps with a pulse position modulation scheme. So what we proposed was, as we have seen in the solid state technological aspect, usage of laser diode will introduce as 10 folds data rate or 10 folds bandwidth. So therefore, we directly went with the laser diode based transmission. So here is the simple aspect of block diagram approach where we use the source, either it can be LED or laser, but we use the laser as the data source, and then we come up with a material called phosphor. So if I'm using blue light, there is a technology called the generation of white light using the blue LED. There is no direct blue LED, white LED available. We should pass the blue light through the yellow phosphor, then it generates the white light. So this is the aspect of technology which require material with the source to generate the uh, illumination source called white source. So this is called aspheric lens to focus the spreaded light from the phosphor. Normally, the property of the phosphor is once the pencil beam of the laser enters, it spreads over an angle. Just to focus this towards the receiver, we need a spherical lens, and or a link lens. What we choose, we place our receiver with a condensing lens or concentric lens, through which we focus to a narrow area photo detector. Either it can be PIN or APD, depending on the technology of use. This is the simple uh, technical representation of or block diagram representation of any visible light communication system is. So what we proposed is laser based, in which this was our setup, which we used for the testing. We used RF data source, bias T to modulate the data on laser. So this was our laser, just use the pointer. This was our laser diode of 415 nanometer, which generates the blue light. And this is the remote phosphor. While passing through this, the blue light will observed as white light. and this is the transmitter lens, and over the free space we are transmitting. This is our test bed, and this will be received over a receiver lens and focused on a photo detector, and then we convert that into RF at the back end and then process the data. So this is with this setup we measured the frequency response of the overall link, which gave us up to 800 megahertz of the bandwidth. So with this bandwidth we tried to transmit on-off keying data, which gave us up to 2.5 into 10 power minus 7 bit error rate with the transmitted power up to 10 dBm. So with this characterization optically for the given test bed, we tried with the bidirectional video streaming to focus how multimedia capability exists in visible light communication. I have a video to show this. So this is the our work was supported by 5G Testbed India, hosted by EC Department IAC Bangalore. This was our prior work in 2019. I just want to play the video. It may take some time to load. Yeah. So the work is multimedia streaming through bidirectional laser-based visible light setup. So this is our block diagram. So normally the bidirectional implies we transmit as well as receive. It's called TRX model. Any device has both the capabilities, like it will act as a transmitter as well as a receiver. In that model, we developed this. What is the interesting thing about visible light based bidirectional is the downlink. That is, we have to see it in the way like this, the access point. If you consider this end as an access point, this end as an access point, which can be connected to our ceiling, and this can be floor side, which is the user device. So if you turn it by 90 degree, you can see that visual way. Because our test bed was flat, we ended up with this kind of setup. So bidirectional in a way, access point, which is transmitting as well as receiving, and the user device, which is transmitting as well as receiving. In the downlink, which is from access point to the user, which should come up with, because my technology is VLC, it should come with communication as well as illumination. Therefore, I should go with generation of visible light communication, that is white light. So therefore, in that way, you can see I'm using the phosphor and the blue laser source. So therefore, I'm getting the white light on my receiver. So that means illumination aspect is covered as well as data is embedded with that white light. So we do the processing, I mean, we receive and then we do the processing at the receiver. So see the uplink part of it. So here we don't have any phosphor in the material. We are using a IR source, and that IR source is not visible by the naked eye. So therefore it is not illuminating the room. The uplink is not illuminating the room, and this is the receiver at the floor side, and it makes sense like this becomes the downlink and this becomes the uplink, and together it's a bidirectional link. So this is our test bed, physical test bed available at ECIAC. You can see here, you can see the white light getting generated, whereas from this side, that is the uplink side, we don't have anything. These are the two high quality videos, HD videos played from either side. You can see the laser source. You can see the bluish nature. After passing through phosphor, it became white light. Then passing through aspheric lens, it is focused to the receiver. The link length we kept was around 2 meters. These are the USRP devices with which we are pushing our computer data and modulated on a laser. And these are the AC coupled avalanche photo detectors. And this part is a downlink path. Here you can see the HD 720p video streaming seamlessly through the downlink setup. Similarly, here with the IR source like 785 nanometer, which is focusing to the receiver, which forms the uplink path. So this is the USRP which is supporting the uplink path. Here you can see the another pin detector used for the uplink path. In the next part of the video, we can see the link blockage. We'll demonstrate the link blockage in it. We'll block one of the link and we'll see how the data transmission stops. So now we'll see, yeah, in this particular path, we'll block the downlink. So therefore you can see the car video is stopped, whereas the bike racer video is continuing. And next one is the demonstration in the absence of ambience light, like in the dark mode, how the transmission happens. I'll show you. I'll stop and pause and show you the setup. This is the setup in the dark mode. You can see the white light generated, whereas in the uplink you will not see anything, but the video transmission is happening in the absence of ambience light, that is the infrastructure light. So I would like to acknowledge DOT for supporting our work. Yeah. So that was the key idea. We covered the multimedia transmission capability of visible light communication bidirectionally. So therefore, this can be an add-on technology for the use case. I mean, add-on technology for the upcoming generation with the use case as MTP, that is mobile telepresence, which supports the hospital monitoring or the telemedicines or robotic surgery kind of applications. The next concept which I took over was like RF VLC coexistence, which I described earlier. Like any new technology cannot obsolete the previous technology. The current technology is RF, VLC is coming in the next technology. They should coexist. And to process them, there is a requirement of handover. That is, when there is one availability and other is becoming weak, there is a need of handover. So with that as a coexistence model, some papers have been proposed, like by the Ash et al. Team. You can see the coexistence model, like RF is there, VLC is there. You may ask why this kind of model. When you are proposing VLC, why are you again introducing RF? I'll describe why it is so. So the reason is we will not encourage RF, but and we will not make it obsolete as well. We'll first support our device with both the technologies. I'll describe why. Because as a device, it can be mobile in nature, and there can be a region where there is no illumination, but I need the data. Then RF can support us. But when it comes to the region of VLC access point, definitely it has all the features like high data rate, low latency and all. So the device will enjoy the VLC link. So then it will not connect to RF. So this is how we have to play with between RF and VLC to enjoy the upcoming technology. So therefore, as I described, it is if I go with RF, it is EMI prone and medical device will not function, and VLC can and directional, so therefore secure. With all these aspects, definitely we should go with both the aspects like RF and VLC coexistence as a current scenario. So these are the different models proposed, like one access RF access point and multiple visible light access points. So this is the traffic model when a device is passing through multiple VLC access points and one RF access point. Like the blue colors dots are all, the triangles are all LiFi access points, and this is one RF access point covering the uncovered region of the VLC access point. So I'll just describe the next work which was done by us, VLC RF handover, with the concept called receiver side channel selection. So this is the model what we had. Like we had a particular, we defined particular geographical area of coverage in our lab, and then we made such that there is a coexistence of RF and VLC zone. This is how we tried to transmit. With the video, I'll make you more understand. So
Sir,
this is what
actually, we are running out of the.
Yeah, it may take hardly 1 minute.
Okay,
Just
thank you.
for the curiosity, I'll just.
Okay.
So this is the transmission. Like I have a dual mode receiver. So like the mobile receiver is moving from VLC region to RF region. You can see there was a breakage, and then you can see the continuity of the video transmission here. So now it is connected to VLC access point. Now when the device moves out of the line of sight communication from the VLC, it goes to RF coverage and the video communication continues. So this particular video is from the RF. Yeah, I think I'm done.
Okay.
Yeah. In conclusion, I have introduced you what is LiFi or optical wireless communication is, so how important that thing with respect to the upcoming wireless communication, what is the particular use case I addressed, and how VLC can be add on for it, and what are our works towards the upcoming technologies to propose. I hope I'm done, and I would like to acknowledge my Professor Varun Raghunathan from ISC and 5G testbed Professor Chandramurthy and Sudhakar for their guidance and support, and Creative team for giving the opportunity to describe my thesis work, part of the thesis. Yeah, I'm done.
Thank you, sir. Sir,
Sorry for audience, I took extra time.
sir, questions are in chat box. We go.
Yeah. The question from Srinath. How does technology aspire to replace mobile tower currently radiating wireless signals? How can light interference affect in terms of medium range data transfer if multiple transmissions? Let me address the first question, like how does technology aspire to replace mobile tower currently radiating the wireless signals? Okay. As I described in the model, we worked on the indoor wireless model. We are trying to replace the indoor access points. So therefore, completely we can make it obsolete. Like RF access points can be removed in future, but as a technology development, we have to go with the coexistence model. So coming to the outdoor model, there is a FS4, free space optical communication, which is another wing of optical wireless communication, which will definitely address the replacement of mobile towers as well. But it is a point to point, but it can work as a long haul. And this optical wireless communication is also supporting V2X, vehicle to vehicle. That way, in future, VLC can replace these mobile towers as well. Coming to the next question, how can light interference affect in terms of medium range data transfer if multiple transfer? Okay, again, it can be like I work on my subsidiary work called NOMA, non-orthogonal multiple access, where we try to multiplex multiple data without any interference. So that NOMA technology with VLC can uh, definitely overcome the interference problem. I think I have addressed. Next one is Dr. Shobha Devi from BMS College is asking, can this technology be used for TV antennas and avoid large space? Yes, as I said, it can be looked good for free space optical communication. So definitely point-to-point solution is possible from VLC. So thereby we can replace the TV antennas as well. But the TV antennas are talking over satellite to the home. In the other way, we can have like point-to-point communication over the earth, any 2 points of the geographical earth points. Yes. I'm not seeing any more questions on the chat box.
1 minute, sir. Allow them to ask directly. One
Yeah.
minute. If any questions, you can unmute and you can ask directly. Any questions? Mahesh, sir. Any comments for the session?
Hello, I'm Dr. Mahesh from Bangalore University. Sir, hello.
Yes, sir. Yes, sir.
Can you hear me? Yeah. So, actually, yeah, the one major limitation is the long distance communication is not possible by this technology. I think that is the one thing, right?
Yeah, people have
Yeah.
addressed. Just to answer
Yeah.
you, people have
Yeah.
addressed with FSO for more than a kilometer, or they addressed up to tens of kilometers. But my major work was to address indoor. That's what.
Yeah, because if you are using the sources like a laser thing, actually laser, highly monochromatic and unidirectional. So if that is the case, suppose if you want to have the network coverage area should be more, then probably the lensing systems are to be introduced, it seems, right? Yeah, then again, will it not become a cumbersome at the, just like instead of our wireless routers, like we need to have like these LiFi routers, like systems. Yeah.
Yeah, as I said, FSO can be an long haul, point to point, back haul.
Yeah, that is yeah.
It can be. It cannot be like covering the multiple users.
Yes. And even if it is indoor, even if it is an indoor, then it will be restricted to only to one ground area, maybe first floor or maybe the ground floor or like that. Because if it cannot be extended to the high, the next higher altitudes or something like that. Yeah.
No. The concept is like whatever the existing lighting infrastructure.
Yes.
That will be embedded with the data. That is what the concept is. So therefore, we have the lighting infrastructure everywhere in each of the room in any building. So definitely we get the data.
Okay, but means that is each room we need to provide the systems.
In the sense, user will be there. Like if you take any office environment, there will be a sitting table, office bench.
Yeah.
So he will be directed with a particular light source. He will turn on his light source. So it means he is turning on his data source as well.
Yes, right. That is
the
thing.
Hotspot for him.
Yeah, that's like it means each area he need to have one source like that. But practically implementation means for a general public, can this be bring it in a commercially? Is it possible?
Yeah, that's what.
because the
It's
type
in
of
the way,
sources,
like
yeah,
it's in the proposal way. Like
yeah,
you can see in this model what I described, like this particular model where people are using it in an office. Like a illumination source is a point beam or a covering as a hotspot. You can see individually they are enjoying the data. Hello? Hello? Hello, sir?
Okay.
Yeah.
Any more questions? Okay. Satish, sir?
Yes, ma'am?
Okay. Shall we wind up, sir?
Yeah, I'm done. If there are any questions, they can reach me offline.
yeah. Just I would like to comment. It's a very wonderful work and wonderful presentation, madam. I
Yeah,
enjoyed.
thank you, sir. Thank you.
Okay. Thank you for joining today. Creative Weekend Talk. Special thanks to our speaker, Dr. Satisha sir, for sharing their insight. Let's continue our exploration together in future session. Thank you one and all. See you at the next Creative Weekend session.
Yeah,
Thank you.
thanks for creative team for giving me the opportunity.
Okay. Thank